So here's an example of the amount of data that we actually captured. And this is just one tier of that data. From vectorization, spatial, which is the three-dimensional aspects, the implementation of time and schedule, the execution, the performance, the sustainability of what we do, preservation of what we do, why we're out in the field actually capturing this, and then how we model that information and data goes into mitigating or managing risk. And these are scan locations layered on top of each other, as I said. Two of those capture points that are key are the goalposts at the opposite ends of the field. We utilize those for modeling purposes, but they also become very critical control points inside of those other hundreds of control points we take throughout the stadium. Because of things like scripting and automation, give the ability to produce or design a building like you see on the right. And with that, I open it up to any QA or any discussions. As Matt said, I'm Michael Warren with AECOM. I'm our Associate Vice President but Director of our Digital Practice and Technology Group. The group was formed about 5 years ago inside of AECOM, and traditionally we had just your traditional surveyors prior to the start of the group. We expanded that into the digital realm. And what I'm going to talk about today is our focus or our emphasis on scan to the model. It's not just a matter of scanning for the sake of scanning to capture information or measurement, but for the production of what the final output is based on a contract deliverable or what is required. A lot of the work that we do is focused on our internal team. We're a company of 57,000 people. 47,000 of those are design technologists or the people that actually produce the work. And then we have outside work that we do for clients. So to start off, people talk about AI and machine learning, and this is a fun slide that I like to bring up because we also, as part of our team, which I'll talk about, we have programmers. And one of the things that people overlook with reality capture is this expectation that we can create things and it'll understand what's going on. I love this slide because artificial intelligence cannot tell the difference between the Chihuahua's face and the blueberry muffin, okay? So be careful of what you're promised and what your expectations are with what you're doing. This is our team. This is our leadership team. We have about 9 different groups inside of our department, and this is another fun little slide because when the company had asked for a photograph of the leadership of our teams, we gave them a LiDAR scan. So it's pretty cool. Now our focus is basically around asset management. So we see reality capture as part of the asset management lifecycle, start to finish, recycle that data, capture that information over a period of time. So we've broken it down inside the company into 8 different phases, and these phases also work into the design portion of what we do. So the first dimension is that scratch pointer conceptualization. So how do we take that into reality capture, and how do we take that into the modeling that we create? Well, what is it that we're doing? What's the whole purpose behind why we're going out and we're doing this? So we have to conceptualize it. But what's more important, and we had to overcome this problem inside of our group, is if we're scanning, what are we scanning and why are we scanning it? And again, it goes back to that model. So our paradigm shift using these 8 steps inside of AECOM is very simple. If you're on the modeling side or the production side, it's mandatory as you join our team or become part of our team that you work in the field with the scanning technicians and our surveyors to understand the process that they go through. But what we've also found is that also translates into better scans, because instead of missing scan data because we're going every 30 meters, the modelers are then educating the scan technicians to get them to understand where to capture those scans to get the best and highest fidelity for the use. That then translates into better scanning plans whenever we're, programming our work. But we go through this life cycle, and there's a slide I'm going to show at the end, the concept of a Mobius strip. But these 8 steps, from vectorization, spatial, which is the 3-dimensional aspects, the implementation of time and schedule, the execution, the actual cost, right? The performance, the sustainability of what we do, and then the preservation of what we do, why we're out in the field actually capturing this, and then how we model that information and data goes into mitigating or managing risk. So here's an example of the amount of data that we actually capture. This is a floor plan view of a rail station. And this is just one tier of that data. Because one of the things that we found is we scan at ground level, we scan at mid-height, and then we use telescopic scanners to go up above the ceiling or very high so that we can capture all of the information. Normally what we do whenever we're inside large facility projects like rail stations or stadiums or airports is we have to build that digital twin that everybody talks about for asset management. So we have to capture everything that is there. What's key is whenever we do this, you heard everyone talk about control points. We don't utilize just one control point. We utilize multiple control points. And whenever we start getting into vertical structures, what's important is with those large-scale infrastructure projects, again, we start outside and work our way inside. Even though the bulk of the work is inside, all of our control is taken from existing monuments or control points that we take outside. And because GPS does not work inside, we translate that and shoot that information from the exterior into the interior of the building. And then we immediately establish the vertical controls throughout the building to put everything on vertical datum. Here's another example, and you see the overlap of these scans. And these are scan locations layered on top of each other, as I said. So a lot of times whenever we scan, we're not taking one static scan at a certain height. We're taking multiple scans over multiple heights, leaving the scanner in the same position. What's efficient about that? And I'm going to talk about that, the equipment, the processes, other things that we use. We have an enterprise agreement with Leica. So all of our equipment that we use when we're in the field and all of our processing and post-processing software comes from Leica. So we have a range from, the handheld BLK to go all the way up to the Leica P50. We own all of our equipment. We get it serviced on a regular basis about every 30 days to make sure that it's calibrated all the time, and we have good control, so it's important to maintain. So when we start talking about projects in these large infrastructure, large-scale entities, how do we approach them? So with stadium modernization and construction, we are a full AEC delivery firm. We also operate and maintain on behalf of our clients. The reason why stadiums are important is because they basically function like cities. They're very complicated to build. There's a lot of infrastructure that goes into place whenever they're planned. So how do we approach stadium modernization or reconstruction? We use Leica C10s, Leica P50s, and then drones. And the types of drones that we use vary. But we use the drones for additional capture, mostly for photogrammetry, some LiDAR scanning, but a lot of our scanning is done terrestrially, and we will use lifts or other means to get the scanners into position where we need them to be. Processing, all of our processing is done using Cyclone. It's just standard. That's what we do inside the company, whether it's unstructured data, but the bulk of what we do is structured data. And then what's important is the downstream deliverable. When I was talking about the model itself, what is the nature of the software that's going to be used? Because that also influences how we do the data capture and something that has to be considered. Different softwares, we have 2 enterprise agreements between Autodesk and Bentley. And the client's contract deliverable dictates what type of software we have to use for that final deliverable. But as we're producing and considering how we take reality capture and consume that information for the use, it's important to think about the end use case of how we're delivering that. So inside of a stadium, this is an example of Sun Life Stadium, that we captured for renovation. And if any of you follow me on LinkedIn, this was one of my teaser images. But what's very interesting here is you can see the numbers on the slide are the control points, and we're in the hundreds. But there were thousands upon thousands of scans taken to be able to accomplish this task. It's just a 3-dimensional example overlaid on raw data that we put in to Civil 3D based off of as-built conditions and then traditional surveying mechanisms as an underlay to the scans so that we were supplementing the information as we were processing it. Now, we had an interesting discussion yesterday with Sean at Autodesk, and he had talked about they ended up with multiple goalposts, for example, with one of the scans that they had done. One of the things we do with control is we use targets, but targets that are set based upon GPS, and two of those capture points that are key are the goalposts at the opposite ends of the field, okay? So they're positioned, they're targets, they're geospatially referenced, and again, we utilize those for modeling purposes, but they also become very critical control points inside of those other hundreds of control points we take throughout the stadium. Here's an example of a LiDAR scan that was taken after the demolition had actually started to occur. And what was important here, and the reason why I'm bringing this up, is because there's never too much data or information. As we saw this morning about the Wrigley Field situation, we had to have just-in-time delivery of prefabricated components to be brought on site and put into place. So tolerances were very key. The use of the software that we had was very key. Understanding the spatial relationships, and you can see in this image that there are 3 control points that we took at vertical layers, and we had to analyze this information in very detailed fashion. What was important about the amount of data that we captured, this was over 100 terabytes of information just in point clouds alone. But how do you get that information to be able to use that much data inside of tools like Revit? It's critical to understand how that has to be broken up in the other software tools and the implications that you're going to use. But this information was important for us as we started to produce drawings. We actually analyzed and utilized the LiDAR information. We didn't remodel this building. We actually designed around the LiDAR data itself to inform what we were doing inside of Autodesk Inventor, what we were doing with those components and parts and elements inside of the use of a tool like Revit. And you can see that we have tolerances down to the 32nd of an inch. We were able to get the project done ahead of schedule, under budget, and on time. And after the renovation was complete, we then supplemented the model with the existing conditions, and that's a Revit representation of the actual physical structure upon completion. And this is just some of the fun we like to have, and we give these images to our clients at the end. This is reality capture morphing in the photogrammetry of the completed project. So what you're looking at are LiDAR scans morphing through the virtual reality aspect of the project, morphing into an actual photograph. Data centers. It's a building, but they're very, very large infrastructure consuming hogs, okay? They take incredible amounts of power, incredible amounts of resources, and when you're doing them, they're exceptionally large complexes that are very complex buildings. Here again, we use the Leica P40 and the RTC 360. That's our standard workflow. Again, processing was done with Cyclone, and then we utilized Revit and Navisworks for the completion of this work. What's interesting here is, again, the point cloud as a deliverable. We have delivered projects to our construction arms in the field where we don't draw the existing conditions in either AutoCAD or Revit. We actually use the point cloud information at very high fidelity and put that information on drawings. What we then do is design around that for the new work. And for this particular data center project, all that we modeled was the new work to make sure that we had no clashes, no interferences, that everything fit inside of the building. So what you see in the colored elements are actually the Revit components that were created using that point cloud as the background and designing around it. We did not model the existing conditions because we already had them. The data was there from the reality capture, so it's more cost effective for us and less time consuming to actually produce utilizing these high density point clouds than charging a client to redo the work. We also turn the point cloud information over to our clients, or typically we end up hosting it for them in our cloud server environments like BIM 360 and giving them access to it, because again, we're talking about hundreds of terabytes worth of information when it's all said and done. These are just some additional images. of that new work, how it's planning and how it's being phased and designed inside the point cloud itself. This is the final build out and the final representation of all the new systems going in, overlaid on top of that point cloud, and this is just one building out of a large complex in addition to the civil site work that had to be done in the underground utilities. And this is the overall campus view with all the buildings, and at this point we had finally modeled the new shells, and again, as it was done, to put them inside of containers and then validate what we were doing. Typically, at the completion of the project, we would use a software, basically, we take ClearEdge, and then we would go back in and validate and model the systems to make sure that we are turning over something to the client for their asset management, just in case they didn't want to utilize the point cloud model itself. Power. These are very interesting projects because if any of you are in that industry or you actually do that work, they talked about it this morning with energy. One of the problems you have with scanning is the drift, because these things move. The power lines are moving, the wind is blowing, transmission lines, the poles are very high. You have to be very careful with your drone flights. But the other thing is the electromagnetic fields that are created around these things wreak havoc on scanners. So it's very important to make sure that you set up and structure your control points, but also where you're scanning. It's critical because I don't know if you guys have ever noticed this, but we've done a lot of transmission work. You can actually see the gaussing or the fields inside your LiDAR scans. And it's noise, but it's very hard to get rid of and very hard to take out of your scan. So it's important to go through these processes in a very systematic way. In this particular instance, we had 1 mile of area that we had to model, basically to look at tree clearances, ground control, the coverings, a lot of rock outcroppings, very, very severe terrain kind of situations. And this was for pre-planning to switch over to another high voltage system by putting up new lines. We used Autodesk Civil 3D, InfraWorks, and Autodesk Revit to create what you're going to see. So again, this is planning, right? Understanding. This is over 1 mile and exceptional high amount of data. But if you know anything about using tools like Revit or Civil 3D, one, Revit doesn't like things that are geospatially referenced. So what's important about the way we work at AECOM is Civil 3D is part of our process with all scanning that we do, because all of our scanning is geospatially referenced. That will create a nightmare for you inside of Revit, and it'll give you garbage when you try to bring those point clouds in because it's outside of Revit's data range. So everything we do starts with a base control point for the modeling that's extracted and then shared from Civil 3D into our vertical modeling environments. It's a very important, critical part of our workflow. But the other thing that's important about that is the tiling of the information. So we not only tile and plan how we post-process that information for consumption by the design teams, we tile and plan how we're going to utilize something that's a mile long, that much data, that much information, very rugged terrain, very hilly terrain, into how we tile the work into Civil 3D. This is not one file. This is over 100 files that have all been brought together and stitched together. So as we zoom in a little bit closer, this is where the Revit kicks in, where we did feature extractions and creations from our automated tools to understand, we program to understand where these things are. Because the point clouds are very vast, you can see the density from the overlaps that we were able to accomplish, much higher levels of density than we would traditionally get with aerial. But what was important here was they wanted all of the transmission information physically modeled. And I don't know if any of you work on the modeling side of what you do, but Revit is not very friendly with flexible things like wires. But these wires have depth and density. One of the things I've been trying to push ClearEdge to do, for example, is to be able to model things like wires or catenary systems, because I believe their software is just at the cusp of being able to do that. Things that sag and things that bend. So I would love to be able to see something like that come out. But we were able to accomplish and tackle this model being very creative. And by very creative, I mean, since we can't model wires physically inside of Revit, we use flexible pipe. And then we use Rushforth tools to reclassify that information and reestablish the parameters that were attached to the information so that it came up as a transmission line. So we were able to put voltage and other information on those physical objects before we turned them over to the client. The other thing was this was a final deliverable. So by using mesh technology, we took the mesh, created the models and the point clouds, and packaged all of that in one container and delivered that to the client in the form of a Navisworks file. So they had all of this data-rich information that was very small and robust compared to the amount of information it took for us to capture it. It's just another, three-dimensional view of the expanse and the challenges that we had. There were roads, there were railroad tracks, there were buildings, there was a water processing plant involved in this, and we extended it beyond where we went, and this was just a limitation of where we cut the point cloud data off at the 1 mile point, because we noticed that once we went beyond that mile, the software couldn't handle it. The computers got unstable because it was too much data to process at one time. Roadway and structures, this is the fun part, because whenever I was hired by AECOM, I'm an architect by trade, but when I was hired by AECOM, I was brought in the transportation sector. And it was because transportation was moving more towards BIM. And they needed BIM management and some BIM protocols to come into place. And this is where it really gets dynamic based on our workflow. Again, we have our big horses out here, the P40, the P50, and again, multiple types of drones. We use drones very selectively, though, because if any of you do TOT work, it's very hard to get approval to fly a drone over a bridge or a road because it freaks people out when they're driving their cars. Also, if you lose control of the drone, there's very high liability if that drone takes out a car and causes, a 20-car pile up on the road. So very strategic use of drones, usually flying below anybody's visual height, and we typically do that on bridges and bridges alone. Everything else that we do on the surface is done with mobile mapping. We do that with a partnership with Mitsubishi with their mobile mapping system, which can take information down to 3mm cracks up to 60 miles an hour. We incorporate that data and that information, again, geospatially referenced, and then supplement that with terrestrial scans. Our final output is Civil 3D, InfraWorks, Autodesk Revit, and then the Bentley products, MicroStation, Open Roads Designer, and Open Bridge Modeler. So here's an example of a forensic study of a road. And we had to go out and scan this, and this was done, again, geospatially referenced, but very high amount of control points with a Leica P50 with well over, just for the small expanse that you see between the bridges and the roads, there were hundreds and hundreds of scans because this was for a forensic study for a lawsuit. We then had to translate that and determine a model to be able to represent those heat maps or the deflections of what was actually occurring inside those existing conditions that couldn't be understood traditionally by looking at just at a LiDAR scan. This is the actual terrain that we were able to derive from the surface. And what's important here is we're not using tools to do the feature extraction to build the terrain. We're interpolating those points, generating those points, and then utilizing them to create the surfaces or the DTMs that we actually use. So when we go back to that original slide with the blueberry muffin and the chihuahuas, there are certain things that humans have to do because humans have a better understanding of how to gather and capture that information than the reliance upon software. This is another example of where we take the integration of a point cloud and then those terrain models where we're trying to represent grading and the actual surface itself in correlation to what's going to become a movable bridge or a movable bridge construction. In this instance, because the bridge was going to be displaced and a new bridge was put in, our deliverables were basically what you see there. A point cloud for the bridges and then the terrain information itself. Now, when it comes to bridges, what's important is a lot of oblique information. And when we do our bridge scans, we do them for preservation or inspection services. So very much like what HDR showed with the dams and monitoring cracking, we do that in a much safer manner by capturing all of that information using terrestrial scanning and using our drone technology. But also we have to supplement that with very high megapixel photogrammetry. And then we too have our own AI system that can detect and determine those cracks, but that we work in conjunction with our inspection teams to do that. New construction for bridges, capturing that asset so that there's something to compare to upon the biannual inspections. It's becoming very huge in our industry that after the construction is complete, the LiDAR scan actually becomes that as-built document that we're turning over to the agencies that they can then go and scan and compare upon their biennial inspections. This is where it gets fun. Historic preservation, we talked about historic preservation with what we saw with CEC, but we also had discussed that. I think one of the questions had dealt with infrastructure and bridges. This is the Northern Avenue Bridge in Boston, so if anybody is here from Boston or familiar with Boston, it's a movable bridge, it's a turntable bridge that hasn't been in operation for over 60 years because the bridge was deteriorating. What was interesting and fascinating about this particular bridge was the structural engineers for the city had analyzed it and had determined that we could not enter the bridge to scan it because it couldn't hold more than 100 pounds per square foot. So we had to find a way to scan this entire bridge to be able to generate and create a model for adaptive reuse or putting the bridge back into service. We were able to scan this with our P50, the RTC 360, and then our P40 from various locations, buildings and everything around, but not on the actual bridge itself. These are actual point clouds of the bridge that we took from the shore, zoomed in, and this is the reason why we've dedicated ourselves and have that enterprise agreement with Leica because of the amount of fidelity that we have inside of these scans. The amount of detailing, you can see all of the rivets, and again, we were not on the bridge physically. Here's a view from the top of a building, and this is why we love the P50, because we were able to get on top of lots of buildings to capture all of this information, but also capture at a very high density level the top of the information for the bridge. And this is just a black and white view of that same perspective looking down planimetrically and the density of the point clouds themselves. Some more imagery. That's the bridge in its fixed position right now. It can't rotate to close to get from one side to the other. Again, very, very highly detailed imagery with regard to this, and it was important because I was the guy that got stuck having to build that. That actually melted the motherboard on my computer because there was so much information, the computer overheated whenever I was working inside of Revit building that, and that's the composition of about 100 separate Revit models where the detail was there all the way again down to the rivets. Now here's where it gets fun. This was something innovative that we did utilizing point cloud technologies. This is an overlay. This was done with 3ds Max, but this is an integration and an overlay of Esri ArcGIS information and the actual point cloud data that I had previously showed you. This is actually something really cool and something that I'm very proud of because we made point clouds move. What's great about sharing that video, and the reason why it's important for me to share it, is AECOM was able to win that project because of the innovative use of point cloud technology. Instead of utilizing the Revit model that I made and getting that to animate or do things with it, we found higher value in the amount of detail that we got from the point clouds to be able to isolate and take that portion of the bridge and make it spin and rotate it back into position. So lessons learned and best practices. So it's important for us. Processing, like a cyclone. We've used dozens of other software applications and platforms to do this, but we found that we get the most power and the most fidelity and the most versatility out of utilizing Cyclone with the amount of data and the information that we capture. Post-processing information. ASTM E57 is our preferred mode. The reason why we do that is because of the letters ASTM. And that's also a requirement for a lot of our government agencies, but we found it to be the most stable platform for us to transfer data, and it does generate a great amount of data. Leica LGS is our second format that we utilize with CloudWorks integrations into our software. Then obviously Autodesk Recap, Context Capture, and again, CloudWorks. And then the modeling use are RCS and RCP, 3MX, 3SM, and then LGS for delivery. This is our workflow. I'm not going to describe it. You all should be familiar with what those icons represent. On the top are the Autodesk products. On the bottom are the Bentley products. But the cool thing is that final deliverable across the top between QPix and HoloBuilder, that is where we take our point cloud information and our modeling information for web viewing by our actual clients, so they can see the fidelity of all the information in one spot, the asset-based information that they're looking for, asset tagging, classification of the point clouds, things like that. Now, what's important for us in these lessons learned is having a board of portfolio management, what we call the digital estate. This is how we take those 8 steps and break them down in actual functional production, and then where the metrics that give us the asset performance, okay, when it's in use, the importance that we find is we start to go off the chart, and that productivity raises itself very high. Again, not from the Revit model, but from the adaptive reuse and understanding of what we can do with the reality capture information. I talked about this at the beginning, the concept of a Mobius strip. And I'm going to close and leave you guys with this idea and this thought and this concept. If you're not familiar with a Mobius strip, it's what you see on the left. But the idea is if you take a pencil or a pen and you start at a point on that strip and you move the strip, you start and end at the same point, and that line is actually on what appears to be both sides of the paper. We take this approach, that 8-dimensional approach, and use that as our life cycle approach to everything that we do, because data is the single source of truth to us, and that reality capture is brought up in data or physical form. And when we talk about digital twins, that Mobius strip, because of things like scripting and automation, give the ability to produce or design a building like you see on the right. And with that, I open it up to any QA or any discussions.